All right, this is an example where the external pressure here is kept fixed as the volume changes. But it doesn't have to be kept fixed. I could change my external pressure through the whole process. And that's the path. We talked about the path last time being very important, defining the path. Right, so if I have a path where my pressure is changing, then I can't go directly from this large volume to this small volume. I have to go in little steps, infinitely small steps. So instead of writing work is the negative of P external times delta V, I'm going to write a differential. dW is minus P external dV, where this depends on the path, depends on path and is changing as V and P change. Right? Now I'm going to add a little thing here. I'm going to put a little bar right here. And the little bar here means that this dW that I'm putting here is not an exact differential. And what do I mean by that? I mean that if I take the integral of this to find out how much work I've done on the system, I need to know the path. That's what this means here. It's not enough to know the initial state and the final state to find what W is. You also need to know how you got there. This is very different from the functions of state, like pressure and temperature. There's a volume, there's a temperature, then a pressure here. There's another volume, temperature, and pressure here, corresponding to this system here. And this volume, temperature, and pressure doesn't care how you got there. It is what it is. It defines the state of the system. The amount of work you've put in to get here depends on the path. It's not a function of state. Okay? It's not an exact differential. So the delta V here is an exact differential, but this dW is not. And that's going to be really important. Right? So if you want to find out how much work you've done, you take the integral from the initial state to the final state of dW minus from 1 to 2 P external dV. And you've got to know what the path is.